I'm an astrophysicist, and I work at an observatory called Jodrell Bank. That's in the countryside just outside Manchester. That's one of our telescopes there behind me. If you watch science TV shows, you might see Darryl Breen or Brian Cox running around at Jodrell Bank. That's where I work. So what do I do? Well, I spend my days using telescopes from around the planet, searching for explosions in space. Yeah. I also look for neutron stars and black holes, which are some of the most extreme and rarest objects in the cosmos. I'm part of a large team that's designing the next generation of telescope to look deeper into the universe and in finer detail than we've ever been able to do before. So that's what I do. Why do I do that? Why would I, or anybody, expend so much time and effort and resources on an endeavor like this? Why would you push technology, engineering, and design to the extreme to pursue questions that are, well, at first glance, a bit detached from our everyday reality? It's because I need to find out the truth. Some people, like Tom Cruise, can't handle the truth. That's a movie reference, can't sue me. But I can't handle not knowing the truth. I need to know the truth, the whole truth, and nothing but. And my contention, my message I'm trying to get across today, is that truth is to be found by looking at the most extreme environments, looking where we're not comfortable, where we don't already know what's going on. This is where we can find new understanding of phenomena that we don't have any grasp on at the minute. Now, I'm an astronomer, so I probe cosmic environments, and I do that with a telescope. I'm a radio astronomer. That just means I use a different type of telescope that can see radio waves. Now, radio waves are just a type of light, and the only difference between radio waves and the optical light you can see me in is the size of the waves. So the light you can see me in is very small, and the wavelengths are something like the thickness of a page of paper or of a strand of hair. Radio waves are much bigger, human size. So Galway Bay FM, for example, that's broadcast on radio waves that are about this size. Okay? It's still 96.8, right? It's about that size. So it just so happens that viewing the universe with radio eyes, you can see it at its most extreme. There's other benefits of radio astronomy. You can observe during the daytime, and you can observe while it's raining. So Galway's produced some radio astronomers. This means that there's no need for me to go to sunny, glamorous locations like Hawaii to do my observing, and I can do it in places like Cheshire or Birr, County Offaly. So they're maybe not glamorous, but they're remote. And an important consideration for astronomers is light pollution. So if you take your telescope and you go into Eyre Square at 2 o'clock in the morning and try and see the sky, amongst the other problems you might have, you won't see the sky very well because of the city lights. If you try and look at the sky in radio waves, similarly, you'll be blinded by mobile phones, microwave ovens, air traffic control, car ignitions, electric fences. The list goes on and on. Lots of things emit radio waves. So remoteness is important, even if sunshine isn't. So I've surveyed the radio sky. I've spent weeks and months and actually quite a few years doing this. And I have made some discoveries. And I'm going to show you one now. I should warn you, though, this is cutting-edge scientific research, which means I haven't a clue what this is. The guy in there said, "Is that your slide, that gobbledygook?" So, any idea what that is? White noise. Yeah, some of it is white noise. I should tell. Okay, I'll tell you what I think it is, and we can examine it. I should tell you what it is first of all. This is 1 second of data from the Parkes telescope in Australia. That's 1 second along the bottom, and then we have short radio waves on the top and longer waves on the bottom. And the keen-eyed amongst you might see this signal, which is there. Maybe you can see it. And you can see that the shorter waves arrive first and the longer waves arrive a bit later, about a second later. Just from this, we can tell a lot. This signal itself, the signal that's buried in that data, lasts about a millisecond. What can we tell from that? Well, there's a speed limit in the universe called the speed of light, and that's 300 kilometers per millisecond. And that's not like speed limits you may have encountered on your way to the town hall today, where maybe you can go 10% over and get away with it. The speed of light cannot be exceeded. It must be strictly obeyed. But the 300 kilometers per millisecond speed limit, what this tells us when we detect a signal that's a millisecond in duration, the thing that produced it cannot be bigger than 300 kilometers in size. And that's much smaller than any normal star or planet or moon. So what we have here is a detection of something very small. Okay. Now this delay can also be understood. And it's because space is not empty. There's dust and stones knocking around. And when light hits these dust and stones, it gets delayed by a tiny amount. But we can measure this delay. In this case, it's a second. And from that, we can work out how much dust the light signal has traveled through, and we can work out how far away it has come from. And it turns out that this signal has traveled a distance of at least 70,000 light years. That's quite far. That's quite far. It's quite far, yet we can still see it. That means it must be really bright. So our detective work has told us we have a very quick explosion lasting about a millisecond. It's very bright, and it's come from a reasonably large distance. What could that be? Well, I need to bring you up to date on some history so that you're appropriately qualified to answer that question. There's this guy called Stephen Hawking, and I don't know if you heard of him. In the 1970s, he was, and he still is, obsessed with black holes. And he realized that mini black holes, should they exist, would emit energy and shrink. Another rather famous astronomer called Martin Rees, he's the UK's Astronomer Royal now. You may have heard of him. He realized that black holes shrinking in this way at some point would shrink no more and explode and vomit forth, they'd vomit forth their energy, all this energy, in an explosion. The only thing is, this explosion would be pretty hard to see because it would only last a millisecond. And it would kind of get scrambled a bit and get delayed due to going through all the dust between us and in the galaxy. But if you had a telescope good enough, you could see that to 70,000 light years, maybe a bit further. Aha. So maybe this is a discovery of an exploding mini black hole. Okay. Now, I'm not the first person to look for these. There's been many searches down through the years. As I said, these were proposed to exist in the 1970s. So people have had a go. And a radio astronomer by the name of John O'Sullivan, who wasn't from Cork, he's Australian, he was trying to find signals like this buried in his telescope data. And in the process of doing that, he invented Wi-Fi. It turns out that trying to find signals like this buried in your data and sending wireless signals from one computer to the next uses the same algorithm. So by searching for and finding mini black holes, we found out, first of all, they exist. If they exist, they must have been formed, but they can only be formed in the early universe. So we've made a discovery about the early evolution of the universe. Now, is that worth pursuing this endeavor? I think it is. And if you disagree, I mean, we got Wi-Fi out of it. That's pretty good. So, yeah, okay, I've got one yeah for Wi-Fi. But didn't get anything for the black hole, but that's okay. So, I hope that shows you one example of why you would search for the most extreme objects in the universe. And that's explosions. I'll give you one more example. of extremes, and that is gravitational waves. Now, there was this guy called Albert, and he made a number of very important predictions about gravity. Now, you probably think of gravity, despite, as well as all the very entertaining talks, gravity is the thing keeping you stuck to your seat today. Tá mé cinse go bhfuil is a glán daoine an seo an focail Gaelach le high gravity. The Irish word for gravity is downtarrinch. That's literally world pull, which I think is a very good intuitive understanding of what gravity is. But Einstein saw some deeper implications for what gravity is. He saw space and time as one and the same thing. He named this thing space-time. He wasn't very good at naming things. He was good at physics. So space-time could be flat, or it could be curved. It could have bumps and hills on it. And Einstein's his key little bit of intuition was that the curvature of space-time is gravity. So maybe if you think of an Irish landscape, you'll understand that if you're on a flat plain, you have no worries of falling under gravity. But if you're on the side of a mountain, you know there's some gravity there just itching to pull you down. But space-time is not exactly like the surface of the Earth. It's more like the surface of an ocean. And there can be ripples that travel through this. And those ripples are gravitational waves. Do gravitational waves exist? They are predicted just over 100 years ago by Einstein. Now, I'm prepared to bet 1,000 euros with anybody here that gravitational waves definitely do exist. Okay, maybe TEDx is not the forum for outlandish gambling. So maybe I'll just tell you how they will be detected, so that when they are, you can say, oh yeah, I heard about that. The way to do it is to understand what gravitational waves do. If a gravitational wave was passing through the Town Hall Theatre today, what it would do is it would make distances shrink and expand, shrink and expand, shrink and expand. The difference in distance is like measuring a meter stick change in length by 1 atom in size. And that's really hard to measure. So what enterprising people have done is they've said, right, let's make a kilometre stick. And then we only have to measure something 1,000 atoms in size. That's really hard to do. But it's not as hard. So how do you measure distances change on such tiny scales? Lasers. It's obvious, that really, isn't it? So what you do is you fire a laser down a tube several kilometers in length off a mirror, and it'll come back to you. Now, I've already said that this laser light will be traveling at the speed of light, which we know must be strictly obeyed. So by measuring how long it takes to go down the tube, bounce off the mirror, come back to you, you know how long the tube is. And if a gravitational wave is coming by, the tube will be changing in length, and the laser will arrive a little bit early, a little bit late, a little bit early, a little bit late, and we'll catch a gravitational wave. So that's one way to do it. The same principle can be applied to clocks. If we had a whole bunch of very accurate clocks and we spread them out in the galaxy, and we watched these clocks tick, and gravitational waves were going by, the ticks would happen a little bit early or a little bit late, a little bit early, a little bit late. And we could use those to detect gravitational waves. So why don't we do that? How are we going to put a bunch of super clocks in space, Evan? Well, we can't do that. But we don't have to, because it turns out there's a whole bunch of them there already. Yeah, it's good. So there are these stars called pulsars. They're discovered by an Irish astrophysicist, actually, Professor Jocelyn Bell. These stars rotate very rapidly, and they emit a beacon of radio waves from their poles, like a lighthouse in space. I could do a demo. So They just emit radio waves like this. And if you point a telescope at them, every time that the radio waves line up with you, you'll see a pulse. So you'll get blip, blip, blip. I'm getting dizzy. Whew. They told me not to sit down. They said they're props. You can't sit on those. So you'll see these blips, and if you can treat these blips like the tick of a clock. So another way to detect gravitational waves is to find all of the pulsars in the galaxy and study their clock-like behavior. And this is a major goal of a telescope that we at Jodrell are working on at the minute. That's called the Square Kilometre Array. With that, I and many astronomers will look into the extreme, weird and wonderful corners of the universe, and hopefully we'll make many discoveries. And I hope we see a lot of gravitational waves. I'm going to finish now, but I'm just going to leave by encouraging you all to explore the extreme aspects of your lives as you go about your daily lives. Seek them out. A wise man once said, "Turn and face the strange." I don't think you'll regret it, and you might find something amazing. Thanks for listening.